This is an overview of the reactions of carbonyl compounds with nucleophiles. And this is something that we did look at a little bit in the alcohol chapter in the context of making alcohols. So this should seem a little familiar based on that. So we can divide carbonyl compounds into two classes for their reactions, and that's why we have a chapter 19 versus a chapter 20. So chapter 19, we have the aldehydes and ketones, and these don't have a leaving group on the carbonyl. So this group Z would be a hydrogen or an alkyl group. In chapter 20, we'll learn about carboxylic acids and their derivatives, and these compounds do have a leaving group on the carbonyl. And sometimes these are referred to as class 1 versus class 2, or type 1 versus type 2 carbonyls. I've seen both. I've also seen the 1 and the 2 mean different things, so I'm going to avoid that terminology. So what happens if you have a carbonyl compound with some group Z, whether that group can leave or not, is that the nucleophile attacks the carbonyl carbon and you get some sort of a tetrahedral intermediate. If this group Z can leave, it does, and one of the driving forces for that is the formation of this stable carbonyl compound. And so we end up with a reaction which is called nucleophilic acyl substitution. So for those of you currently in Chem 24, when you did the Diels-Alder reaction, that was what happened after the Diels-Alder reaction. Important thing to notice here is you get the carbonyl back. If this is not a leaving group, then one of the things that can happen is that you can just protonate this oxygen and get that. This chemistry is somewhat complicated by the fact that various things can happen once you get to this point, and I'll talk a little bit more about that next. This chemistry is complicated somewhat by the fact that occasionally, and this is what we saw in the alcohol chapter with the reaction of esters with reducing agents and Grignards, is that this carbonyl can then undergo a second reaction. So again, the carbonyl group is a source of electrophilic carbon that therefore reacts with nucleophiles. And you can see that by looking at these two resonance contributors. In the second resonance contributor, you actually have a positive charge on that carbonyl carbon. So if we look at the relative reactivity, and I've put everything from chapter, the aldehyde ketone chapter and the carboxylic acid chapter together on this. So it turns out that acid halides are the most reactive, followed by anhydrides, followed by aldehydes, followed by ketones, followed by esters and carboxylic acids, followed by amides. So the aldehydes and ketones fall in reactivity between these two and then this group. As far as, for now, the relative reactivity of aldehydes versus ketones, this is a mix of steric and electronic effects. So hydrogen is smaller than an alkyl group, so sterically it's easier to attack an aldehyde, and it would be even easier to attack the one aldehyde where you have two hydrogens, that would be formaldehyde. There's also an electronic effect. Alkyl groups are more electron donating than hydrogens. We know that because alkyl groups help to stabilize carbocations. And so if the R group is mildly electron donating, that's going to make the carbonyl carbon less electrophilic. We'll look into the factors that go into this when we delve into the carboxylic acid and derivative chapter. But for now, we're going to continue on with the chapter 19 material, which is the aldehydes and ketones, which have no leaving group. So we can break these down a little bit further into quote-unquote basic conditions where you have a strong nucleophile and acidic conditions where you have a weaker nucleophile. So we have basic conditions and we have acidic conditions. All right. So if you have basic conditions, again, strong nucleophile, so this is going to be something like a Grignard or a hydride reducing agent or an alkoxide. This is a good enough nucleophile that it's going to, and I've written it with a negative charge because they all kind of sort of effectively do as they attack. It's going to attack the carbonyl carbon directly. We get this tetrahedral intermediate, and then in a second step it gets protonated. And when we do these reactions, the nucleophile and the proton transfer step are separate steps, so you have to write them as a 1, 2. You can't just blithely combine a strongly basic nucleophile with an acid and not expect them to neutralize each other. And so again, this is what we saw with aldehydes and ketones reacting with Grignard reagents and hydride reducing agents back in the alcohol chapter. We added a hydrogen or a carbon and got an alcohol. That's probably the easier of the two. Under acidic conditions, we have weaker nucleophiles, and with the weaker nucleophiles, they need a proton transfer in the first step in order to make the carbonyl more electrophilic. So in other words, this on its own is not electrophilic enough to react with things like alcohols, water, thiols, amines, and related compounds. And the reason I have an asterisk here is because I've written it as a primary amine, but it really can be anything that is ammonia, a primary amine, a secondary amine, or we'll even see some examples where these are not strictly speaking primary amines, but primary amine-like things like hydrazines. And I did an example of that in the reaction one, which was the one that turned out to have sound. So what's going to happen here, the purpose of the acid catalyst is it protonates the carbonyl carbon, and you get that, and then that has a second significant resonance contributor, which is clearly more electrophilic than the original carbonyl. So now the nucleophile attacks, and a feature that all these nucleophiles have is that they have a hydrogen on the nucleophilic atom. So that's going to attack. And remember that anytime you have a nucleophile that has a hydrogen on the attacking atom, that you get this species, which then is going to have to lose a hydrogen in order to get to the final product. So again, anytime you have a nucleophile with a hydrogen on the attacking atom, you always have a final proton transfer step. And then I've written here, further reaction depending on the nucleophile. So for example, with alcohols, you can get an SN type reaction to go from a hemiacetal to an acetal. And with the amine nucleophiles, you can get an elimination, and it's going to depend whether you eliminate across the carbon nucleophile bond, if that nucleophilic atom still has a hydrogen on it, or if you eliminate across the carbon-carbon double bond.